Welcome to the Deep Dive. We're the show that takes these really complex ideas, sifts through all the research, and then tries to hand you the most potent nuggets of knowledge.
That's the goal.
And today, wow, we're diving into an idea that's so fundamental, potentially so transformative, it might just redefine everything you thought you knew about, well, our own planet, and really our entire solar system. What if, just imagine, a huge chunk of our world right here beneath our feet isn't what we thought it was? Like imagine Earth having an invisible twin.
It's a concept that genuinely challenges our foundational models, doesn't it? It pushes the boundaries of, conventional astrophysics and planetary science.
Right.
For decades, the whole idea of dark matter, its presence, was largely seen as this abstract thing way out there, a distant galactic phenomenon influencing galaxies far, far away.
Yeah, spinning galaxies and all that.
Exactly. But this new perspective, it brings it incredibly close, weaves it into the very fabric of our immediate cosmic neighborhood, right here.
That's the core of it, isn't it? That shift, it's huge. So our deep dive today is into Earth's dark plasmaspheres. Pretty revolutionary concept, championed by a researcher named J. Alfred. And we're going to sift through some truly fascinating research. I mean, from incredible insights coming from neutrino oscillation data, from those massive detectors like IceCube and Super K.
Yeah, the scale of those experiments is amazing.
To these strange, subtle little anomalies picked up by our own satellites orbiting Earth. Our mission really is to try and figure out why our long-held understanding of dark matter density right here in our solar system has been, well, frankly, grossly underestimated.
And crucially, what that means, what this reevaluation means for us, for the ground we stand on, and, for how we understand planets everywhere, really.
Okay, so prepare yourself for this. This is the big number, the one that really reshapes how you think about our home planet. Recent analyses, the very ones we're looking into, suggest that the sheer mass of dark matter in and around our entire Earth could be as much as 20% of our planet's total mass.
20%?
Yeah.
That's not trivial.
20%.
Yeah.
Can you even begin to wrap your head around what that means? For our planet to be like 1/5 invisible, it's like finding a whole hidden layer to Earth.
It really isn't just a subtle adjustment, is it? Or some small refinement of the models we already had. This is, well, it's a fundamental reevaluation of Earth's composition. It demands a complete rethink of what even constitutes a planet and how we measure its most basic properties.
And it gets even more intriguing. This dark matter, it's not just some, nebulous, floaty stuff out there.
Right.
It's believed to be in a specific state, an energetic state, a plasma, forming these invisible structures the author calls dark plasmaspheres that actually interpenetrate our familiar world.
So not just diffuse particles, but an actual state of matter, a dark plasma.
Exactly. So if it's not just this vague stuff, but it's in a plasma state interpenetrating our world, what exactly is a dark plasmasphere? And plasma will definitely unpack all of that.
Yeah, that's a key part of this whole picture.
For the longest time, I mean, when we talked about dark matter, we pictured it way out there, right? Distant galaxies affecting stars, galactic rotation.
Large-scale structures.
Yeah. The prevailing view was that the density of dark matter here, on or around Earth, was incredibly low, almost negligible. In our calculations, it often just got, conflated, mixed up with ordinary matter because our methods couldn't really tell the difference.
That conflation is a really important point.
But this deep dive, it challenges that historical view head on.
And what's truly fascinating here is how these new technologies, they're letting us peel back layers of assumptions we held for a long time. See, for so long, our mass measurements relied mainly on gravity.
Right. Newton's laws, gravitational pull.
Exactly. The problem is gravity doesn't care if matter is ordinary, the stuff we see and touch, or dark matter. It just feels the mass. So it measures the sum of both. If something has mass, gravity acts on it. Visible, dark, doesn't matter to gravity. This new research, though, using something called neutrino oscillations, gives us a completely independent way to look at it.
A different tool entirely.
Precisely. And it's showing dark matter isn't just some distant galactic thing, but potentially an intimate, substantial part of our cosmic neighborhood. Right here.
And that's where the game changer comes in. That 2023 analysis. The one based on those neutrino oscillations from IceCube and Super K. That's the breakthrough that gives us that, well, staggering 20% estimate for Earth's dark matter. It's a number that literally rewrites the textbooks.
It really does. It forces us to reconsider the very makeup of the celestial bodies we thought we understood so well, from the sun to the planets, including our own Earth.
Now, this wasn't like a sudden out-of-the-blue thing. This idea that we might be underestimating dark matter locally, it's actually been brewing for a while.
Right. It didn't just appear overnight.
Jay Alford, the researcher whose work is sort of the basis for a lot of this discussion, he first raised concerns about this underestimation way back in 2007. He was essentially asking, are we really sure we're getting this right? What if we're missing something fundamental here?
And those initial whispers, those questions, they started to gain some real scientific traction. It showed a growing curiosity, I think, within the community about just how close this dark matter might be.
Absolutely. Then came some truly groundbreaking work in 2008. This was by Jinkao Zhu and Jonathan Siegel from the University of Arizona. And their findings were, well, genuinely astounding. They estimated the dark matter density around our sun
Yeah.
to be approximately 16,000 times higher than the background density you find out in the galactic halo.
Wow, 16,000 times higher. Not just double or triple, but
Right.
okay.
Just think about that for a second. 16,000 times. That's not a small tweak. That's a massive shift in our understanding of dark matter right here, locally.
And the sheer quantity they calculated is equally staggering. Hughes and Siegel estimated, get this, 7.69 times 10 to the 19 kilograms of dark matter had become gravitationally bound just within Neptune's orbit.
Okay, that sounds like a huge number, but how does it compare?
Well, for perspective, Earth's total mass is around 5.97 times 10 to the 24 kilos. So 10 to the 19 is much smaller than Earth's mass, but, and this is the key point, it's about 300 times greater than the background galactic halo mass you'd expect to find in that same volume.
Ah, okay, so compared to the average out there, it's way, way denser here.
Exactly. It means our solar system has basically acted like a gravitational magnet, concentrating dark matter way beyond the cosmic average.
That's a huge difference. And the implications, Hughes and Siegel saw this immediately. They were crucial, not just for, actually trying to detect dark matter particles directly.
Because there's more of it around to find.
Right. But also as a potential explanation for those weird spacecraft acceleration anomalies we've seen. The flyby anomaly, they call it.
Ah, yes, those slight, unexpected speed changes.
Exactly.
Yeah.
Tiny, unexplained speed boosts or drags as spacecraft swing past Earth. They've baffled scientists for years.
And their conclusion really nails this shift in thinking. They stated, and I'm quoting here, overall, we find that dark matter in our solar system is far more important than previously thought.
Far more important.
Due to gravitational three-body interactions between dark matter particles, the sun, and the planets, a significant amount of dark matter winds up gravitationally bound to our solar system. Dark matter may therefore prove to be profoundly important in our solar system for both its additional gravitational effects on planets and other orbiting bodies, as well as the motions of spacecraft. It really highlights how dark matter could be directly influencing things we can actually observe right here.
Right under our cosmic noses, as you said.
Yeah.
And this wasn't just, one study that got ignored. This idea was backed up. Stephen Adler, a physicist at the Institute of Advanced Studies in Princeton, he and his team corroborated this in 2009. They specifically linked these higher local dark matter densities to those exact same space probe speed changes, the flyby anomaly. Adler basically said the observed anomalies required dark matter densities many, many orders of magnitude greater than the standard galactic halo density to even explain them.
And Adler introduced a really useful concept here, this idea of an accumulation cascade.
Accumulation cascade, like a
Yeah.
chain reaction.
Exactly like a chain reaction. Think about it over the solar system's 4.5 billion year life. Any initial dark matter that gets captured gravitationally makes it slightly easier to capture more dark matter. It's like a snowball effect.
Okay, makes sense.
This builds up the density rapidly, and crucially, this whole scenario relies on an assumption: matter-antimatter asymmetry within the dark matter itself.
Like we have in our universe. More matter than antimatter.
Precisely. Just like our visible universe has way more matter than antimatter, which is why we're here and didn't just annihilate ourselves at the Big Bang, the theory suggests dark matter also has this asymmetry. Very little dark antimatter.
Why is that so important?
Because if there were equal amounts of dark matter and dark antimatter, they'd just annihilate each other as soon as they got close, like when they were gravitational captured. Poof, gone. We wouldn't see this massive buildup over billions of years. The asymmetry allows it to stick around and accumulate.
Got it. So if that's the case, this cascade of earthbound, solar system-bound dark matter would mean the density right here is way higher than the galactic average. Like our little corner of space is a dark matter hotspot.
That's the idea, a densely packed region in an otherwise much more diffuse cosmic sea. And this thinking gained more traction, leading to some really intriguing proposals about our whole galactic environment.
Yeah, like in 2012, Sylvia Garbari and her team at the University of Zurich, they used a revised way to measure mass, looking at thousands of key dwarf stars near the sun.
K-dwarfs.
And they found that the previous methods had consistently underestimated the amount of dark matter. When they applied their adjusted technique to real data, their calculations strongly suggested dark matter almost definitely exists around the sun, and there's like a 90% chance it's more abundant than we thought.
Which is compelling evidence.
It
And it
is.
led straight to that fascinating proposal of a dark disk within our galaxy. This concept was championed by Lisa Randall, the theoretical physicist at Harvard, and her team.
A dark disk. So not just a halo, but a flatter structure.
Yeah, Garbari noted their findings could be the first evidence for this dark disk. Or maybe it just means our galaxy's main dark matter halo is sort of squashed or flattened locally, which would also boost the density near us. The dark disk idea proposes this pancake-like structure of dark matter embedded within the bigger spherical halo.
Okay.
And the author, J. Alfred, he suggests that much of the dark matter in this hypothetical Randall-Reese dark disk, especially the stuff close to ordinary matter, would likely be self-interacting and possess a weak, get this, dark electric charge.
Whoa, hold on. A dark electric charge. What does that mean? Is it like, regular electricity?
Not quite. Think of it more like a super, super weak version of our everyday electromagnetic force. Much, much weaker.
Okay.
This dark electric charge, if it exists, is why dark matter particles don't easily clump into atoms like our normal matter does. It explains why it's mostly invisible and doesn't form complex structures. But it could still allow for very gentle interactions between dark matter particles themselves, making it self-interacting just within its own dark sector.
So it can interact with itself, just not strongly with us.
Pretty much, that's the idea.
So what does all this mean for you listening? It means the very space our solar system is cruising through might be far, far denser with invisible matter than we ever imagined. And it could even be shaping our galaxy in ways we're only just starting to figure out. It's not just some abstract theory out there. It's right here, potentially influencing everything from galactic shapes down to tiny movements in our own solar system.
And we started seeing even more direct hints closer to home. Not from stars miles away, but from our own hardware orbiting Earth.
Yes. Back in 2014, Professor Ben Harris from Texas University, he looked at data from a whole network of global positioning satellites.
Oh.
The US GPS, Russian GLONASS, European Galileo.
Right, the navigation systems.
Exactly. These satellites orbit at different heights, from about 5,000 kilometers up to 35,000 kilometers. Harris used their precise acceleration data, basically measuring Earth's mass as felt by each satellite at its specific altitude.
Okay, using them like little probes.
Yeah. And he concluded that Earth has more mass than the official number established by the International Astronomical Union, the IAU.
More mass than we thought.
Yeah. And since the ordinary matter we know about in that region, the thin atmosphere, etc., couldn't possibly account for these tiny anomalous accelerations, these little extra tugs, the presence of dark matter was inferred as the only plausible explanation. It was like the satellites were feeling an extra gravitational pull from something invisible.
That's fascinating. One of the earliest hints from direct observation that maybe Earth itself is heavier than our ordinary matter models predicted. A little whisper that our standard measurements might be missing something big.
So, okay, given this new picture, higher dark matter densities, constant interaction, the big question is, how does it get here? How does all this invisible stuff accumulate on and around Earth? Well, it turns out there are quite a few proposed sources, and some are really dynamic. It paints this picture of a constantly changing cosmic environment.
Yeah, exactly. We're not just talking about some static distribution that's always been there. It's more like a dynamic inflow. The solar system is constantly interacting with its galactic surroundings, leading to what you could almost vividly call dark matter weather patterns.
I love that phrase, dark matter weather patterns.
Yeah.
Like, for instance, Jörg Diamond, a physicist at UC Santa Cruz, suggested back in 2005 that these smallish, sort of flattened sphere or cigar-shaped clouds of dark matter, about 4,000 AU. Remember, an AU is the Earth-Sun distance they regularly pass right through Earth.
Regularly. How often?
He estimated these huge, diffuse clouds drift through our area roughly every 10,000 years. And an encounter could last maybe 50 years or so.
Okay, so not constantly, but recurring.
Right. Now, even though these clouds are enormous, their densities are incredibly low. So the gravitational effect on Earth's orbit is tiny, nudging us by less than a millionth of a meter per second. No big orbital shifts.
Still, it highlights this constant low-level interaction with invisible structures passing by.
Exactly.
Yeah.
But it's not just pure dark matter clouds we need to think about. There are also ordinary matter clouds that are thought to harbor dark matter too.
Right, like the local interstellar cloud. That's a big cloud of neutral hydrogen gas that our sun and Earth are actually moving through right now.
We're in it.
Yep. We entered it about 100,000 years ago, and we're expected to be inside it for another 10,000 to 20,000 years. And researchers like Leo Blitz from UC Berkeley and David Spergel from Princeton, they believe these huge, diffuse interstellar clouds aren't just ordinary gas and dust. They think they're actually teeming with dark matter, like cosmic incubators for it.
Wow. So Earth has been soaked in this mixed cloud of ordinary and dark matter for a big chunk of its recent history, constantly interacting with both. And this immersion, it goes way beyond just this local cloud, right? It connects to our whole journey around the galaxy.
And here's where it gets really interesting. This paints a truly mind-bending picture of scale and interaction over cosmic time. Back in 2008, Yu and Siegel, those University of Arizona physicists, again, they estimated that during its 4.5 billion year trip around the galaxy,
Okay.
our solar system would have plowed through an incredible 203 solar masses worth of dark matter.
203 suns worth of invisible stuff.
Exactly. That's the equivalent mass that Earth and the whole solar system has been immersed in and passed through over billions of years of galactic travel.
Okay, visualize this for me. Our solar system is orbiting the galactic center at, what, something like 220 kilometers per second.
That's taking speed, yeah.
So as it's hurtling through this invisible sea of dark matter particles in the galaxy, it's constantly getting bombarded. It's almost like dark matter is just raining down on us. A relentless, pervasive shower of invisible particles. Think about this. Every single kilogram of matter on Earth over its entire 4.5 billion year life has probably encountered something like 1,000 dark matter particles per day.
Every day for billions of years.
Yeah. That's an absolutely incomprehensible number of interactions over cosmic time, a constant whisper of the unseen.
And beyond just this general rain, we also see more structured flows, these streams. Astronomers have observed the Milky Way actively gobbling up smaller dwarf galaxies.
Right, galactic cannibalism.
Pretty much. Like right now, our galaxy is in the process of consuming the Sagittarius dwarf galaxy. And as the Milky Way's huge gravity rips stars from this smaller galaxy, it's not just tearing away the visible stuff, it's also ripping away its dark matter, creating these vast, long streams.
And according to Heidi Newberg, an astrophysicist at Rensselaer Polytechnic Institute, we might even be able to eventually observe a kind of dark matter highway, streaming in one direction right through Earth because of this.
Wow.
It really shows the dynamic, almost violent nature of dark matter in our local area, flowing like these unseen rivers through space.
But maybe the biggest player in accumulating dark matter right here, locally, might just be the most familiar object in our sky. The sun.
That's a compelling thought. I mean, the sun's the most massive thing around here by far.
Yeah.
It makes sense it would act like a giant gravitational vacuum cleaner for dark matter.
Precisely. The sun is, what, about 27,000 light years from the galactic center. It sits right inside this massive galactic dark matter halo, and its orbit around the galaxy sweeps through an enormous amount of dark matter.
And we can even tell it's there, right? Because the sun's moving faster than it should.
Exactly. It's revolving around the galactic core about 60 kilometers per second faster than it ought to, based just on the gravity of the visible matter we see. That extra unexplained speed, that's attributed to the gravitational pull of all that invisible dark matter in the galactic halo.
Okay. And this idea of the sun collecting dark matter isn't brand new either, is it?
No, not at all. As far back as 2001, researchers like Elidio Lopes and Joe Silk from Oxford, they believed the sun held this huge reservoir of dark matter particles. They argued that any massive body, especially a star, would just naturally capture passing dark matter gravitationally, pulling it into its core.
Makes sense.
Lorenzo Iorio and his team in Pisa reinforced this. They suggested dark matter density would naturally be highest around massive things like stars and black holes, basically, wherever gravity is strongest.
So it logically follows that the sun, speeding through the Milky Way's dark matter halo for billions of years, must have accumulated truly vast amounts.
And here's a really compelling image to picture. The dark matter inside the sun would effectively be an invisible sun growing inside the visible sun.
An invisible sun.
Wow. And this accreted dark matter would actually increase the sun's effective mass over time, which would subtly change the orbits of the planets, including Earth, over cosmic timescales.
Change our orbit. How much?
Well, some estimates suggest that if the accretion continues at the same rate it has in the past, Earth's orbit could actually shrink to about half its current distance in the next 4.5 billion years.
Shrink by half. That's huge. Is there any evidence for that?
Remarkably, yes, there's apparently observational evidence for this shrinkage, although it's incredibly subtle right now. It just appears as a slight long-term tightening of the planetary orbits.
Okay, so this isn't just some wild theory then. Physicist Subra Sarkar and Mads Franson at Oxford back in 2010 reached a similar conclusion. They estimated the visible sun could contain about 2 to 5% of its visible mass just in the form of dark matter.
2 to 5% is significant.
It is. And this again relies on that assumption of matter-antimatter asymmetry in the dark matter sector, like we talked about before.
Right, to stop it from just annihilating itself upon capture.
Exactly. Without that asymmetry, any captured dark matter would just vanish, poof, leaving no trace. It needs the asymmetry to stick around and build up into these big reservoirs.
And this accumulated dark matter, it's not just sitting there doing nothing. It might actually be solving some long-standing mysteries about the sun, which is one of the really exciting parts.
Like what?
Well, for instance, the solar composition problem. There are these slight disagreements between the elements we observe on the sun's surface and what our theoretical models predict should be there.
Okay.
Stephen West and his colleagues in London ran simulations. They showed that light dark matter particles, once they get sucked into the sun's core by gravity, could actually transport heat. They'd move heat from the incredibly hot core out to the cooler surface through these very weak interactions.
So they slightly cool the core.
Exactly, which subtly decreases the core's temperature and brings the models into better agreement with observations.
So it's like an invisible internal cooling system for the sun. That's wild.
Pretty much. And similarly, Aaron Vincent and his team in Spain looked at heavier dark matter particles. They proposed these heavier particles could absorb energy in the hottest part of the core, then drift to cooler regions like the outer layers, and deposit that energy there.
Redistributing heat again.
Right. And this energy redistribution could potentially explain the solar abundance problem, which is another discrepancy in understanding the sun's insides. Vincent really highlighted that the main advantage of asymmetric dark matter is that a lot of it can accumulate in the sun because it doesn't annihilate. He noted if it was self-annihilating, it would disappear long before it could move enough heat or energy around to make a difference.
So it's not just about it being there. It's about it actively influencing things, solving real puzzles we have about our own star.
Yeah.
But wait, all these theories about dark matter accumulating in the sun, influencing ordinary matter, they all need this currently yet undetected short-range attractive fifth force. Yeah.
That's the linchpin, yes. This hypothetical fifth force is key to these models. It's purely theoretical at this stage, but it's needed to make the interactions work.
Okay, so what is this fifth force supposed to be like?
Think of it as a very, very subtle handshake between ordinary matter and dark matter, something totally separate from gravity or electromagnetism.
Like a whisper between the two worlds.
Exactly. Imagine trying to push a giant, incredibly heavy boulder using only the force of, say, a feather. That's kind of the scale of weakness we're talking about for these interactions. It's just enough to exchange a tiny bit of energy, maybe carry some heat through collisions, or allow a very gentle attraction between them.
But not enough to cause big, obvious effects or make them stick together like normal matter.
Precisely. It allows dark matter to subtly influence ordinary matter without being easily spotted by our usual detection methods.
Okay, so if we connect this to the bigger picture, it really suggests this profound interconnectedness, doesn't it? Between the visible and the dark parts of our universe. Processes we always thought were purely ordinary matter might actually be influenced by dark matter in ways we're only just starting to grasp.
It pushes us beyond thinking of dark matter as just a source of extra gravity. It becomes an active, if subtle, participant in cosmic events.
And it's not just about the sun collecting dark matter. Some theories even suggest the sun might produce its own dark matter particles.
That's another line of inquiry, yes. One popular candidate particle is the axion, this hypothetical, very light, slow-moving dark matter particle.
Right, axions.
The CERN Axion Solar Telescope, or CAST experiment, is actively looking for these. They're searching for hypothetical axions that might be emitted directly by the sun, hoping to see signs of them converting into photons that we can detect.
Okay, this leads to another really intriguing idea, the concept of a dark solar wind.
Ah, yes. We all know about the ordinary solar wind, right? That constant stream of charged electrons and protons blasting out from the sun, filling the solar system.
Yeah, it causes auroras and messes with satellites sometimes.
Exactly. It's basically plasma expanding from the sun's corona, driven by intense heat and guided by magnetic fields. Now, the hypothesis is, if the sun really does have this large dark matter reservoir inside it, then it's possible that self-interacting dark matter particles could also be ejected in a continuous flow, forming a dark solar wind.
A wind of invisible particles. What would push it out?
Well, the idea is it would be propelled by dark radiation, think of it as the equivalent of light, but in the dark sector, and potentially guided by dark magnetic fields, which would be separate from our familiar magnetic fields.
So these dark forces and dark radiation, they're purely within the dark matter realm. They don't directly interact with our instruments.
That's the theory. They're part of this hypothesized dark sector with its own set of particles and forces, and these interact only very, very weakly, if at all, with our ordinary matter sector, except maybe through that subtle fifth force we talked about.
Wow. And the scale of this influx, if it exists, it's incredible. Trillions, literally trillions of these self-interacting dark matter particles from the sun could be flooding this tiny Earth every single second. A mix of hypothetical things like axions, dark photons, maybe even dark protons and dark electrons.
It paints a picture of our planet being constantly bathed in invisible matter streaming from our own star, not just drifting in from distant galaxies.
So, okay, putting all this together, all these potential sources of dark matter from the galactic halo, from the sun itself, from these passing clouds, it really strongly suggests there's a local excess right here in our solar system, significantly more than the galactic background average.
Yes. We're inside the Milky Way's dark matter halo and maybe even inside that Randall-Reese dark disk. Both of those would naturally contain a higher density of this self-interacting dark matter.
Which naturally leads to this common assumption that's shaped our thinking for ages. If there was all this extra dark matter in the solar system, surely the planet's orbits would be off. They deviate noticeably from Newton's laws of gravity.
Right. And the fact that we don't see big, obvious deviations has historically been used as an argument against having significant local dark matter. It seemed pretty straightforward.
But the author, J. Alfred, he argues that this assumption is just wrong. And this is where that crucial idea of conflation comes back in.
Explain that again.
His point is, if the planets in the sun already contain significant amounts of dark matter inside them, then the masses we've historically measured and recorded for them already include that dark matter. Our past measurements simply conflated, unknowingly combined the dark matter with the ordinary matter.
Ah, okay. So any extra gravitational pull caused by dark matter inside Earth, for example, was just mistakenly attributed to ordinary matter because our instruments couldn't tell the difference.
Exactly. This is a really crucial distinction, isn't it? If our mass measurements were always measuring the total mass visible plus invisible, then our Newtonian calculations would still work out correctly for that total.
Precisely. Gravitational experiments, as that 2023 neutrino study points out, they do not distinguish between normal matter and DM dark matter. They just measure the sum of both. So if a big chunk of what we've always called mass is actually dark matter, then Newton's laws would still seem to hold true for the total measured mass. The laws aren't wrong. Our understanding of the composition of that mass was just incomplete.
And the all conflation, this mixing up, it's even more likely if there's something called a particle-to-particle correlation.
Oh, my God.
Like a dark proton corresponds to an ordinary proton, a dark electron to an ordinary electron.
A mirroring between the sectors.
Yeah. If that correlation exists, maybe through that fifth force again, it would cause a really close link between the two types of matter. So wherever you find a lot of ordinary matter, you'd likely find a corresponding amount of dark matter right there with it.
Making them stack together, effectively.
Exactly. Which increases the chances of this conflation happening totally unnoticed by our traditional gravity measurements.
Okay, to really hammer this home, try this thought experiment. Imagine, just hypothetically, the sun and all the planets were made entirely of dark matter. No ordinary matter at all.
Okay. Pure dark matter objects.
But, and this
Yeah.
is key, let's say they still had their currently accepted masses. The exact masses we use in all our orbital calculations today. If
Yeah.
that were the case, they would still obey Newton's laws perfectly. Their orbits, their rotations, everything would look normal. No significant anomalies.
Wow. So the fact that we don't see obvious anomalies doesn't actually rule out significant dark matter inside these bodies.
Exactly. It just means our historical mass measurements inherently included it as part of the total gravitational tug all along.
Okay, so it's not just about dark matter passing through our solar system then. The research suggests that this self-interacting dark matter might actually lose energy as it interacts, however weakly, with ordinary matter particles right here on Earth.
Maybe facilitated by that fifth force, causing some mutual attraction, however slight.
Right, which implies Earth itself acts like a giant filter or maybe a trap, increasing the concentration of these self-interacting dark matter particles within it, not just around it.
And this buildup isn't just happening now. It could be ancient. The idea is that embryonic dark matter might have already been present when the solar system first formed.
How so?
Well, as that primordial gas and dust cloud that eventually became our system was swirling around, it might have been moving through that hypothesized Randall-Reese dark disk.
Ah, picking up dark matter from the star.
Exactly. This early dark matter could have been gravitationally locked inside the cores of Earth, the Moon, and other bodies right as they were forming. That 2023 research study even mentioned that while there are strong limits on how much ambient dark matter Earth captures now, they said, exotic scenarios like the formation of Earth around a DM dark matter seed may still be viable, similar to the formation of galaxies around DM cores, meaning Earth itself might have formed around a pre-existing clump of dark matter, building up ordinary matter on top of it from the very beginning.
Wow, forming around a dark matter seed. And where would this dark matter end up inside Earth? Where would it accumulate?
Well, the gravitational force inside Earth is actually strongest at the boundary between the mantle and the core, about 2,900 kilometers down. So if gravity alone was the only factor, maybe a lot would get trapped there.
Okay.
But if that fifth force is also at play, causing dark matter density to correlate with ordinary matter density.
Then it would go where the ordinary matter is densest.
Precisely. Which means the mass density of dark matter would be highest deep in Earth's core, where ordinary matter is densest, and much less dense up here in the crust or atmosphere. This fits perfectly with that idea of a particle-to-particle correlation, dark proton to ordinary proton, making them essentially stacked together in the densest spots.
Okay, that makes sense. So it suggests dark matter could indeed be trapped deep inside Earth's core. And just like the theory for the sun, it would have been continuously accumulating there for billions of years, slowly but surely increasing how much is inside.
And physicist David Peat actually did a calculation suggesting Earth's core could contain as much as 10% dark matter, or shadow matter, as he called it.
10% just in the core. Think about that the very ground you stand on, the deep core of our planet, might be this dense, incredibly active repository of an invisible substance we're only just starting to really quantify. It genuinely reshapes our understanding of our own home, from its deep interior all the way out to how it interacts with the cosmos.
And this brings us right to the crucial point. How are we actually starting to detect and quantify this hidden mass? How are we moving beyond just inference to actual measurement?
Exactly. Because for so long, our main tools for measuring Earth's mass were these traditional gravimetric measurements. We figure out Earth's mass using Newton's law, and by precisely measuring gravitational acceleration around the planet with super-sensitive gravimeters.
Right, they detect tiny variations in gravity.
Yeah, and those variations are then attributed to the distribution of mass down below. But, like we keep saying, these methods historically just assumed that the acceleration was only due to ordinary matter. They couldn't tell the difference.
And that's precisely where the conflation problem lies. That 2023 study confirms it directly. Quote, gravitational experiments do not distinguish between normal matter and DM dark matter. Simple as that. They measure the sum of both.
So any dark matter contribution was just automatically bundled into the total mass estimate. Impossible to separate it out with those tools alone.
What about seismic waves? Don't they tell us about the inside of the Earth?
They do, yeah. Seismic waves from earthquakes or artificial sources, they travel through the Earth. And by analyzing how they reflect, refract, change speed, seismologists build up this detailed picture of Earth's internal structure and density at different depths.
Okay, so that seems more direct.
Well, yes and no. They tell us about density and structure, but they don't directly measure the Earth's total mass. To estimate total mass from seismic data, scientists still have to rely on those gravimetric measurements and also Earth's moment of inertia, which itself is calculated using the previously measured total mass and radius. So even with seismic waves, that misattribution, that conflation of dark matter with ordinary matter, it still applies because the foundational mass numbers come from the gravity-based measurements in the first place. It's circular.
Plus, there are always uncertainties, right? Even with the best seismic models, there's like a 5% uncertainty in the mantle's density, and it's even higher for the core, sometimes 10, maybe 15%.
And these methods usually don't even include the mass of the atmosphere or the magnetosphere when they define Earth's mass, so it complicates getting a really precise, complete measurement of all the matter making up our planet. These are big blind spots when you're trying to account for something invisible.
But then came the revolutionary breakthrough, a completely new way to look, offering an independent window into Earth's hidden mass. In 2018, Earth's mass was measured using a totally new method, neutrino tomography.
Neutrino tomography, okay.
This method is truly groundbreaking because it uses only weak interactions. It's completely independent of any gravitational measurements.
That is huge, because neutrinos, unlike gravity, they sense both ordinary and dark matter density inside the Earth, right? Because both types of matter feel the weak force.
Exactly. The weak force, one of the 4 fundamental forces responsible for things like radioactive decay, it allows neutrinos to interact very subtly with other particles, both ordinary and dark particles. It's a completely different lens to view Earth's composition through, totally free from the conflation problem of gravity. Okay, so how does it work? How do you use neutrinos to weigh the Earth?
It's ingenious, really. It uses a phenomenon called neutrino oscillation. Think of neutrinos as these tiny ghost-like particles. They're incredibly abundant, constantly zipping through everything, stars, planets, you, me barely interacting at all.
Right, the ghost particles.
But here's the trick. As they travel, they can subtly change their flavor or type. This is called oscillation. And the probability of them oscillating, changing type, actually changes depending on the density of the matter they pass through.
So the denser the stuff they go through, the more likely they are to change.
Essentially, yes. So using these massive detectors like IceCube buried deep in the Antarctic ice, researchers captured neutrinos arriving from different angles, meaning they had traveled through different layers of the Earth to get there.
Okay.
By precisely measuring how many neutrinos came from each angle, and crucially how their flavors had changed after that trip through Earth, the team could figure out the densities of various segments inside the planet. And from that, they could calculate the total mass of Earth and its core, and even confirm the core is denser than the mantle, all without using a single gravitational measurement. It's pure weak force physics, giving us this kind of X-ray vision of Earth's unseen interior.
That is incredible. And the latest findings from 2023, based on how much these neutrino oscillations deviated from what we expect.
Meaning how much they changed compared to if Earth was just ordinary matter.
Exactly. Those results are described as highly significant. The IceCube data, just from a one-year set, it rules out more than 32% of the core's mass, or 24% of Earth's total mass, being dark matter, at the 1 sigma statistical level.
And then there's the Super K experiment in Japan, Super Kamiokande. Using atmospheric neutrinos, their data rules out more than 21% of the entire Earth's mass being dark matter, again at 1 sigma.
So putting those together, the consensus estimate.
The consensus estimate, combining these powerful, independent results, lands around the idea that the mass of dark matter in and around the entire planet might be about 20% and maybe around 30% just in the core. And as the research states, this is highly significant. It's a remarkable convergence of different data pointing to the same revolutionary conclusion.
So this raises a huge question.
Yeah.
If these numbers hold up, it fundamentally changes our compositional models for Earth, and presumably for other planets too. It implies this deep, intimate connection with the dark matter filling the cosmos. It forces us to revise not just what's out there, but what's in here, making up our very home.
Yeah, absolutely.
So,
okay.
We've established there's likely a lot more dark matter in and around Earth than we thought, and it's continually building up. But what is this dark matter actually like? What are its properties? The author, J. Alfred, argues that the dark matter interpenetrating Earth largely exists in a plasma state. Not solid, not liquid, not gas, but plasma.
And that's not just a random guess. There are several pretty compelling reasons proposed for why it would be in a plasma state, all coming from the hypothesized basic properties of dark matter itself.
Okay, like what?
Well, firstly, these self-interacting dark matter particles are theorized to be much, much smaller and lighter than ordinary matter particles. like protons and electrons.
Okay, tiny and light.
Yeah. Now, imagine trying to build a brick wall, but your bricks are incredibly tiny, almost weightless, and they're so far apart they hardly ever bump into each other. It would be almost impossible to form a solid structure or even a liquid one.
Right, they wouldn't stick together.
That's a bit like dark matter particles. Their tiny size and the vast distances between them mean collisions are super rare. This makes it almost impossible for them to bind together to form neutral atoms or molecules like ordinary matter does. They just stay unbound, freely moving. Much like a gas, or more specifically, like a plasma, which is basically an ionized gas.
Okay, so their nature prevents clumping. What else?
Secondly, that dark electric charge we mentioned earlier, the one these particles might have, it's thought to be much, much weaker than the electromagnetic force we experience.
The force that holds our atoms together.
Exactly. In our world, that strong force binds electrons to nuclei, forming atoms. A much weaker dark electric charge means much less stickiness between dark matter particles. This drastically reduces their ability to form stable, neutral dark atoms, again pushing them towards remaining in a plasma state instead of forming solids or liquids.
Not enough glue, basically.
Pretty much. Thirdly, in these hypothetical dark sectors, it's believed there's a preponderance of neutral dark matter particles. This is kind of the reverse of our ordinary matter sector, where charged particles like electrons and protons are common.
So mostly neutral stuff in the dark sector.
That's the idea. And this abundance of neutral dark particles acts like insulation. It slows down interactions between the charged dark particles that do exist, further hindering the formation of solid or liquid states. It's like having lots of empty space or inert stuff preventing the active bits from clumping.
Okay, that makes sense too. Anything else?
And finally, the author even suggests that dark sectors, maybe because of different evolutionary paths in some hypothetical multiverse,
Oh, multiverse. Okay.
might actually be at a higher fundamental temperature than our ordinary matter universe. Higher temperatures mean more energy, the particles are zipping around faster, more energetically.
Harder for them to settle down and bind.
Exactly. Makes it even harder for particles to bind into atoms or condensed states. So this would perpetually keep them in a plasma state, almost regardless of their environment.
Okay, so putting those together, tiny size, weak self-interaction, lots of neutral particles, maybe higher temperature.
Based on all those factors, the logical conclusion is that if there are these spheres of dark matter interpenetrating Earth, they would consistently be in the form of plasmaspheres. These are what the author calls dark Earths. It's like an invisible twin world made of plasma, existing right alongside and within our own, interacting only very subtly.
An invisible plasma twin. And this idea, it stretches way beyond just Earth, right? It opens up some truly mind-bending possibilities for studying planets outside our solar system, exoplanets.
Absolutely. Think about the implications for exoplanets. Yang Bai and colleagues from the University of Wisconsin-Madison in a 2023 study, they're actively searching for what they call dark matter exoplanets.
Dark matter exoplanets. What would they look like? How would we even find them?
Well, they hypothesized these planets might have properties that just don't fit our current understanding of how ordinary planets form. For example, if they're extremely dense somehow, they might show up in measurements as an exoplanet that's denser than iron, but without any obvious ordinary matter reason for being so compact.
Okay, super dense anomalies.
Or the opposite could be true too. You might find one that's so low density that its existence is impossible to explain with normal planet formation models. It might look almost like a diffuse cloud that still somehow exerts a gravitational pull. These are the kinds of cosmic oddities that could hint at something beyond our standard models.
Imagine that. Not just an invisible sun inside our sun, or an invisible Earth inside our Earth, but entire dark exoplanets out there, potentially challenging every single assumption we've made about how planets form and what they're made of. This just opens up entirely new frontiers for cosmic exploration.
And these very low density, maybe radiation-like dark planets, if they exist and are mostly plasma, they wouldn't significantly mess with the orbits of other planets in ways we could easily detect.
Right, their gravity pull would be spread out.
Possibly. And because they interact so weakly otherwise, they'd be incredibly hard to spot gravitationally using our current methods. They could remain largely hidden from even our most powerful telescopes.
It's an incredible thought, isn't it? That the universe might be filled with entire classes of objects that are essentially invisible to us right now, but could be just as numerous, maybe even as impactful as the visible ones we see.
It truly expands the definition of what might be out there.
Wow, what an incredible journey we've taken today. We started with this really radical idea that dark matter isn't just some distant abstract thing, but potentially a fundamental interwoven part of our very planet and our solar system. Our deep dive has shown how our traditional understanding of mass and composition might have been, well, hugely underestimated, a picture that was only half complete.
And that 20% estimate for Earth's total mass being dark matter, that's just a monumental shift in perspective. It changes everything.
And the key to finally unlocking this hidden mass seems to be this transition away from the traditional gravity-based measurements, which, as we saw, inherently mix up dark and ordinary matter.
The conflation problem.
Exactly. Moving away from that towards the revolutionary insights coming from neutrino tomography.
This new method, relying on the weak nuclear force and the weird, subtle behavior of neutrinos instead of gravity, it's finally letting us distinguish and hopefully quantify this hidden mass deep inside Earth's core and its surrounding layers.
It's really a testament to how new tools, new ways of looking at things, can completely redefine our cosmic understanding, literally changing what we thought our own planet was made of.
So as you go about your day, maybe think about this. If our own planet really is significantly composed of dark matter, and if that dark matter is in a plasma state, how might this dark Earth, this invisible twin, be affecting subtle processes we don't even understand yet, right here, right beneath our feet?
Could it be influencing deep geological processes? Or maybe even the environment that supports life in ways we haven't conceived of.
Or perhaps it's even foundational to phenomena we haven't even discovered yet. What does it truly mean to live on a planet that's maybe 20% invisible?
It's definitely a question that could keep you pondering for a long, long time. We really hope you've enjoyed this deep dive.
Yeah, fascinating stuff.
We'll see you next time.